Good evening, everybody. I hope you weren't standing in traffic too long for those of you that were trying to get here. I think there's still a few people on the way, but we'll go ahead and get started. Again, welcome to the Chesapeake, welcome to the Chesapeake Biological Laboratory. I know I see a lot of familiar faces, so I know some of you were here last week, so I'll keep this short. But for those of you who are new, we were founded in 1925 by Reginald Truitt. We are actually coming up for our 100-year celebration, so there's going to be lots of activities for next year to celebrate that. So keep watching our social media site, and we will have our open house again in September again. So we are the oldest state-supported marine laboratory on the East Coast, and we're one of 6 constituent members of the University of Maryland Center for Environmental Science. And we're a pretty unique university that we actually have a mandate from the state to provide advice to the state in terms of things like fisheries management, how many fish can you catch, oysters, and also addressing ecosystem restoration and providing advice to our state managers and regulations concerning the health and of the Chesapeake Bay. So we're not just working on the Chesapeake Bay, though. We're a world leader in the science of coastal environments, their watersheds, and also in graduate education. And we have some wonderful graduate students that you're going to hear from in a minute.
Are they going to swim?
I don't know, I hope not. So this is the second in our series. We run these science and community series every spring and fall. And there are a series of 4 lectures, and the theme for this fall is on long-term monitoring research and the importance of it. And so they'll be speaking to some of the data that is from the Patuxent River, from our pier that has been collected for many, many decades. So these are free public seminars. You can join us here in person, or usually you can join virtually. We will have a couple more after this. Where is he? I just saw Ryan. There's Ryan. Ryan will be our speaker next week, talking about if any of you have walked along the front and seen some scientists in there with a big toe. Every week I say we, I don't do any of it. I just watch. So they're with the net and they're looking at the fish that they're catching in the net, and that's another example of a long-term data set that tells us something about the changes that are happening over time. And finally, I think Jessica is at the back, and she will be speaking on October 29th. So there's another long-term monitoring program of terrapins. I mean, who doesn't like our iconic diamondback terrapin? They have a site that they have quite a large population at the Patuxent Naval Air Station that they've been monitoring. And I'm not going to give the game away, but Jessica will be speaking to issues of climate change and shoreline erosion. So talking of long-term data sets, anybody who's here locally, so this was a couple of weeks ago, right in front of the Tiki Bar. For 2 weeks, we had flooding like this in front of the Tiki Bar. It's not too bad if the flooding is in the morning, because we have 2 ways coming in the island. But if the other weeks was happening at 4 or 5 o'clock, and we only have the one way off the island from here, and that's right in front of the Tiki Bar, and that was flooded. And so this is just an example. All of our data from the pier is on our Patuxent Centennial website. Real-time live data, you can go in and look to see, well, if you want to know chlorophyll, if you want to know the jellyfish, if you want to know temperature. But I love this one. This one tells me if I can come into work or not. And so this is your sea level, and they have marked the red line there, says when we're expecting it to flood by the Tiki Bar. So you can see this is that two-week period, and every high tide is above that line. And so there's right by where you came in, there's the desk. There's a page with all our QR codes that I've been talking about. So you can take one of those and go check out our Centennial website. This is also a wonderful site. If anybody is doing a science project, or you can download the data and work with that as well. And it allows us to come up with signage like this. So this is, you all just drove past it. This is the water temperature from our pier. and it's over the 83 years. We take a global average, and then it's a heat map. So the cold here. So if the temperature that year was -2.5 degrees colder, it's a really, really dark blue. If it's only 0.5 colder, it's light blue. And the same thing for the hot. If it's 0.5, it's orange. If it's 2.5, it's that dark color. Take home message, there's no words, you don't need it. You can just see from 1943 up to, I think this is 2017, you can just see what the trend is. You can see the trend to warming waters over that period. And then the last thing I wanted to chat about was our Chesapeake Dolphin Watch. We talked about this. How many of you have seen dolphins here in the bay? And how many of you have the app? I hope you all kept the hand up. Excellent. So this is a wonderful community project. We know so much more about dolphins now in these 8 years, these programs we've been running, because of people like you. Download the app. It's a free app on your Android or iPhone. When you see a dolphin, whether if you're walking along and you see it on Solomons, or if you're out on a boat, let us know, send us a picture. Our scientists verify that it is actually a dolphin. And you can see all of these different sightings now. We're seeing them way further up in Baltimore, in the north part of the bay. We're seeing that they're coming in earlier each year to the bay as well. But this is just a fantastic program that is relies on you all helping inform us scientists on what the dolphin population looks like. And then finally, to our wonderful graduate students, we have a great graduate program here. It's the Marine Environmental Estuarine Sciences program. It's run jointly with UNCES and College Park, and it's a very innovative graduate program. It's interdisciplinary in its nature, and the whole focus speaks to our university mission that it solves real-world problems. It's an environmental problem, and our students will look at addressing that and trying to provide actionable solutions to that problem. And so after graduate career here, we have many, many examples, hugely successful graduate students in the private industry, in the NGOs with heads of NOAA program, and some of them come back to academia as well. So this is just a plug to try to support our graduate students. They need your support. They are going to be tomorrow's environmental leaders. And of course, we have a lot of environmental problems that we have to deal with. So there's a QR code to help, to donate and help support their studies. So thank you. And with that, I would like to introduce our graduate students. I'm not going to say anything about why they are here. They're going to introduce what they did in the curriculum that led to this talk. So I'd like to introduce at the end there, Alison Dreis. She is at CBL here. Also Amir, also here at CBL. Anna Hildebrand at the front here, also at CBL. And online, you can't really see. We have Fardis, who is actually at the University of Maryland Eastern Shore. So that's the one thing about our MEES program. It is actually inter-institutional. So we have students from College Park, we have students from here, we have students from our sister labs, Horn Point, Appalachian Lab, University of Maryland Eastern Shore, UMBC, UMB. And so it's a great program that it brings students from all sorts of disciplines together to help solve these problems. And then Saida, sorry, last but not least, we have Saida. So with that, I am going to turn it over to our graduate students to tell you all about some work that they did in a recent class. So thank you, everybody.
Thanks, Paris.
I'm gonna try this.
Is it working?
Yes.
Yeah. Good evening, everyone. First, I should have a big thank you to Karis for the kind introduction, and to all of you for being with us here tonight, whether you're joining in person or tuning in on Zoom. And I should say we're grateful to have both the community and our colleagues from CBL here with us. I don't know if you caught the late 1970s song that was being played here as we were coming in. love is like oxygen. But tonight we're going to talk about something even more essential to our own Patuxent River, and that's oxygen itself. As you see, we're so excited to present a story of oxygen variability in the Patuxent River. We're going to start with introducing the course that led to this research. We're going to talk a little bit about that. Then we dive into some historical context of oxygen in the river and go through the causes of low oxygen events in the Patuxent mainly. We'll explain some, I can say, ways of measuring the changes of oxygen level in the over this space and time. And at the end, we're going to put all together by talking about why all these matter to you, I mean to all of us and the local community. I think we're ready to start. And as Karis introduced us so well, I think we can skip reintroductions. No need for me to say that I'm Amir. And I'm gonna pass it over to Anna to start.
You can that one. Good choices. All right, so Karis talked about this a little bit, but I just wanted to give, can everyone hear me okay? Okay, just making sure. But I just wanted to go over the MEES program a little bit myself as a student. So as Karis said, we're all a part of this Marine, Estuarine, and Environmental Sciences program, or the MEES program for short, since scientists love their acronym. So MEES program is kind of the flashy title. So again, as Karis mentioned, this kind of involves a lot of University System of Maryland institutions like College Park, like University of Maryland Center for Environmental Science, and like University of Maryland Eastern Shore, where one of our presenters is tonight. And so as a part of this MEES program, one of these key foundational areas that we're assessed on is taking this something called an issue study group class. And the goal of this class is really to research, discuss, and synthesize information on a current environmental science or policy issue. So we all signed up for the one that was offered in spring of 2023 that focused on this long-term change in the Patuxent River Estuary. And that was taught by Drs. Ryan Woodland, who's over there in the back that'll be presenting next week, Dr. Laura Lapham, Dr. Laura Harris, if you caught her presentation last week, and Jeremy Testa. And as a product from that class, we actually published a paper this past August in the journal Estuaries and Coasts. And so today we'll be going over what we found and what it means for the future of estuaries in the context of climate change. So Bernie Fowler, a long-serving Maryland state senator whom this building is actually named after, remembered it as a river of goodness and kindness that gave fish, crabs, and oysters as nourishment during the Great Depression. He said, quote, "You stood on the sand and could look in the river and see big jumbo crabs 20 feet away, hidden in the grass or behind an old tin can," end quote. Dirt roads and a rural landscape surrounded the banks of the Patuxent River until everything started to change in the 1940s. So rapid population expansion in the area brought thousands of workers down to the Patuxent River Estuary. And as you can see in this figure, there was a lot of change in the Patuxent River from 1850 to 1994. And just to kind of orient you a little bit, the green is forested land, the brown is residential, the red is urban, and then the yellow is land used for agricultural purposes. And so from 1850 to 1953, you can really see this shift from primarily agricultural to more of a shift to this agriculture and forested with a little bit of urban kind of sneaking in. A similar trend exists going from 1953 to 1972. Again, you can see kind of this expansion of forested area as well as more urban land kind of creeping in. And then by 1994, the watershed is much more urbanized. And because of this change in land use, the river began to change as well. Quote, "We've seen grass come and go," people said of the life-giving underwater grasses. "It'll come back. But we've never seen it zero before, never seen water so cloudy and crabs so scarce." End quote. By 1970, the Patuxent River had become one of the most polluted on the East Coast. But through environmental activists in the area, legislation has been enacted and enforced to protect the health of the river. So how has the river responded? In this talk, we'll examine how the health of the Patuxent River has changed over time from 1985 to 2021, why it's changed, and what this means going into the future. Moving forward, I will be your narrator tonight to guide us through questions that will help to tell a story about the Patuxent. All right, and so you may have heard of the so-called dead zone in the bay. Well, there happens to be one that's in the Patuxent River too. And as a part of this course, we quickly realized how large and persistent this dead zone is and how it's been expanding. And so this kind of spurred us to investigate why. But first, let's talk about this whole oxygen depletion aspect. To begin, we'll watch a short video on hypoxia, and then Fardis will explain what exactly that means and what causes it.
All right, thank you, Anna. So based on what was shown in the video, hypoxia means when the oxygen concentration is less than it should be in the water. When hypoxia occurs or when there is less oxygen, it is hard for marine creatures to breathe and survive. And this will lead to what we call dead zone, where life can no longer thrive. Looking for what causes this hypoxia to occur, one of these factors that causes hypoxia is when the warmer water, as shown in the next slide. Yeah, thank you. When there is a warmer water, and that means when the temperature goes up, the water is not capable to hold the oxygen, leading to the lesser oxygen in the water body. And so there will be less of that oxygen available for marine ecosystem to survive. And the other factor that causes hypoxia is excessive nutrient loading. Excessive nutrients, extra nutrients, particularly like nitrogen or phosphorus, which are coming from sources like agricultural runoff or wastewater or industrial activities. When this enters to the water body, they act as a fertilizer, prompting to the rapid growth of algae, the one shows in the video as in the surface of the water. And these algae at the first place may seem harmless, but when they die and they will go through the bottom of the water, the problem starts when the bacteria that decomposes these algae, they need to consume lots of oxygen. So they have to take this oxygen from the water body, and leading to the lesser dissolved oxygen in the water body itself, and ultimately hypoxia, which can consume a large amount of oxygen and leading to the death of lots of marine creatures. And the other factor that is causing the hypoxia is the more rainfall and river flow. Yes, even rainfall and river flow can have a negative impact in the oxygen concentration. That is, when there is more rain and river flow entering to the water body, they can also carry nutrients with themselves entering to the water. And So when there is more rainfall and more of this river flow, there will be more of these nutrients entering to the water body, and that excessive nutrient loading problem occurs. So basically, more rainfall and river flow are just worsening the nutrient loading problem. And also, when there is rainfall and river flow, because they are an external forces and sources entering to the water body, they can alter or manipulate the oxygen concentration in different depths of the water, and making it hard for creatures in specific depths of the water to get the enough oxygen they need. And just their aquatic ecosystem will be disturbed.
Great, so a lot of the factors that Pardis just talked about may apply to a number of estuaries, not just the Patuxent River Estuary. So different estuaries may have different primary drivers of hypoxia. So how do these drivers relate to the Patuxent River? You want to plug your? Huh? She can use that.
Okay, so in the Patuxent River, we have two types of different water that come here. We have lower density fresh water that normally floats on top, and then we have the denser seawater, bay water that comes in that floats on the bottom. Normally, when these waters are mixed, oxygen can mix throughout the water column and also exchange with the air. So you constantly have oxygen replenishing the water column. However, what's been going on recently is we're seeing an increase in fresh water as well as a temperature increase. So this is creating a stratified water column. So oxygen can't pass through the water column, and then oxygen can't exchange with the air in the water. So we're losing oxygen. And as you can see, so the graph you're looking at here is the annual discharge in the Patuxent River. And as you can see over time, it has been increasing. So with that influx of fresh water, we're also getting we should be getting an influx of nutrients. However, that wasn't the case. Nitrogen actually slightly decreased, and then phosphorus stayed the same. But when we look at stratification, we can see the results of that influx of fresh water. So overall, stratification is increasing, but when you look specifically at summer stratification, it's much more intense than the other seasons. In addition, we're seeing summer temperatures that are much higher, water temperatures in the summer in both the bottom and the surface. So we're seeing an increase in stratification and an increase in temperature. So overall, the amount of oxygen that's allowed into the water is greatly decreasing. And as a result, that's greatly impacting hypoxia. So what you're looking at here is a graph of hypoxic volume days. This is a metric we use to gather both duration and space of hypoxia in one representative number. And as you can see over time, yes, it has fluctuated, but it is on a steady increase. That being said, hypoxia itself within the Patuxent River generally follows a pattern. So what you're looking at here, these are the stations where we collected our data, our oxygen data, our nutrient data, and our chlorophyll data. So I want you to focus on LE 1.1 and Brooms Island, and you can see what happens. So that's where it starts. This is late May, and then it begins to expand downward towards the bay. It'll go upward too for a little bit. And then you can see by mid-July, most of the south portion is hypoxic. And then slowly hypoxia starts to break up around August. And then by late September, hypoxia is completely gone. This is the normal pattern that it follows most years.
All right, so now that we know what this hypoxia or low oxygen is and what causes it in the context of the Patuxent River, why exactly is this bad for the health of the river?
Such a great question.
So going back to what Ferdis just explained, they need oxygen to breathe, I mean, just like us. So fish, oysters, crabs, all of them depend on oxygen to survive. And as Alison showed, these low oxygen events are more common in the bottom layer of the sea, the estuary, the river, I mean, the bottom layer of the stratified water. And here you can see some benthic species, the bottom dwelling species, creatures that live in the river floor. I'm using river and estuary interchangeably here. Maybe I shouldn't, but we are talking about the Patuxent, and I think we are on the same page. These benthic species are really important to as a food source for fish and some of them for us. You are kind of familiar with some of them, clams, crabs, the most famous one, and the oysters are really common, some of them as food. In Maryland, we are big fans of seafood. And yeah, some of them are directly foods like crabs and oysters. So these are essential to the food web, and they live on the bottom layer. So those low oxygen events really affect them. And when they don't have enough oxygen to breathe, they struggle, and when they die, that's a bad news for fish, for the whole ecosystem, and for us too. So the answer to that question could be the low oxygen events could affect the very foundation of, I can call, visible life in the estuary. But yeah, as Alison described, hypoxic volume days, or HVD, is an index that shows how long and how big hypoxia lasts. And bigger HVD, higher HVD means that hypoxia, these low oxygen events, are lasting either longer or larger or both. And we see that higher hypoxic volume days correlates with lower benthic biomass. Means that when the hypoxia index is increasing, that bottom dwelling organisms are struggling, and their population and their biomass is decreasing. And this is answering that question, that why low oxygen is so harmful, because it's destroying the whole ecosystem. And now that I've answered that question so precisely and so nicely, I want to know if you have any other questions.
Yeah, actually, I think we should back up for a second. How exactly did you measure hypoxia?
Such a nice question. And surprisingly, I'm ready for that. We didn't go through this before. Yeah, these measurements involves both field work and lab work. There are research cruises like the Chesapeake Bay Program cruises, or our own CBL PAX cruises, where we or they collect samples from the bottom and the surface of water. And having those samples, we can draw these vertical dissolved oxygen profiles and have a picture of how dissolved oxygen concentration changes with the depth of water. Then those samples would be brought back to the lab. This syringe is representing lab work, maybe not greatly, and it's a little big, but in the lab, we analyze those samples, and we are thinking about some other water quality parameters like nutrients and chlorophyll. We measure those. And after that, there's a quality control and assessment of those data that will happen by the scientist, like this casually dressed scientist using laptops. So there's a serious computer work involved too. We have this picture of the Yellow Springs instrument YSI sounds that I can say these are another tool to measure oxygen concentration in the water. There are sensors attached to these sort of instruments, and they could be put in the water for a long time, and they continuously monitor some parameters like dissolved oxygen. And these are the things that we are using at CBL and the CBL peer to have a continuous monitoring of some parameters in the publicly funded project that Karis just explained in the beginning of this talk. And we can have those kind of continuous measurements of dissolved oxygen that are really helpful to gain a deeper understanding of how Patuxent is changing in terms of oxygen. So yeah, just to put the thing together, this mixture of sampling and sensor data gives us a detailed picture of how dissolved oxygen is changing in the water.
Right. Thanks, Amir. It's great that, we have all this data and that a lot of it is publicly accessible, like from the Chesapeake Bay program, for example. And then we can start to tease apart what's been happening in the river over time as a result. But I'm starting to wonder how this will help environmental managers, why we should care about this, and what we as regular community members can do moving forward.
So with the results that we found out, that might help as an insights for the future stakeholders. So for example, the information that we found out in the research might help the environmental organizations for planning, policy making, and making effective decisions on the impact or the extent of Patuxent to have some idea about it. It can also help making effective decisions for the local managers, the groups and the fisheries of conservations that might work to reduce the nutrient pollution, and also how to improve the water quality, and that can help in making an informed decision about it. And also making some targeted action, for example, planting buffer zones or improving the water quality data. This might help guiding the restoration efforts as well. And as mentioned before, the long-term monitoring data that's been working on and ongoing, our research and data might help with the long-term monitoring, as well as this might put some little bit information on the areas that we might need to focus more or need to do some more intervention on. And also last but not the least, giving some information to you guys and the local groups and the community to make a more collective sense of responsibility to work towards the well-being of the river. So as an individual, about the research or the impact or about hypoxia, why should we care about this and what can we do? Well, we all know that river is an important part of our ecosystem and our biodiversity. And healthy river means supporting the local fish, the crabs, as we mentioned before, all the benthos, and in some way, in all improves the ecosystem and the biodiversity of our Maryland area, and it is kind of a part of our identity and community. So we need to take care of the wildlife and the local fishes and crabs, but it's not just about the wildlife. Clean water ensures the healthy river ecosystem and the environment so that our children can safely play, swim, and enjoy the river. And some way our future generation can also benefit with this. And a thriving river can boost our ecosystem, and also it can support the local businesses that are related to this on the outdoor. So as an individual, what we can do about it? Well, we can reduce or eliminate the fertilizers in our home garden so that the harmful runoff that degrades the water quality might be reduced a little bit. We can pump out our septic system periodically. There are so many local cleanup river events that might happen near our community. For example, Alliance by Chesapeake Bay, St. Mary's River Watershed Association. This makes so many initiatives to clean the riverbanks and remove all the litter and debris. So we can join them and make effort to work toward this, and also supporting the policies and the community programs focusing on the development of the situation. And last but not the least, raising awareness is key. Knowing this information, sharing this with your friends, family, and neighbors, so we can all make a collective efforts towards this.
Great. And with that, we would like to acknowledge a few people and organizations that made this work possible. Firstly, Drs. Jeremy Testa, Laura Lapham, Ryan Woodland, Laura Harris, and Kian Jing for your continued guidance and support over the process of writing this paper over the course of the semester, and just being great mentors. We would also like to thank the U.S. Geological Survey, the Maryland Department of Natural Resources, and the U.S. EPA Chesapeake Bay Program for the use of their monitoring data. More specifically, we would like to thank Chesapeake Bay Program's Integrated Trends and Analysis team for their helpful feedback, as well as David Austin, Andrew K. Light, and Walter Boynton for sharing their knowledge about the river during our class. Lastly, we would like to thank the MEES program for providing the support for making this class happen. And with that, I would like to leave you with this quote from the late Senator Fowler. "The fear I have is this. I remember my daddy and my brother catching as many as 30 bushels of oysters in a day. Our family one day caught as many as 25 dozen soft-shell crabs. Those that follow me don't have anything. They don't have a recall, because obviously they weren't here when those things were prevalent. There's nothing in the computer that's going to tell them about that. They'll look at the river and say, man, that's a beautiful river. And I can still run my jet skis and I can still water ski. And my kids can still wade out in the river. I'm afraid they'll start accepting it for what it is. I don't think there will be this burning desire to set the bar high enough. That would be a monumental mistake." And with that, I would like to thank you all for coming out tonight. Thank you for allowing me to be your narrator. And with that, we are happy to take any questions.